Okay, so let's get back to it. Does everybody, everybody needs to get up their TensorFlow collab notebook that we had last time we were working on. Yeah, we ended with plotting, right? We plotted the images and we put it in a random number for fun, right? To pick. Let's share my screen and I'll show you what I mean. Okay, so we were right here. By the way, remember, once you open your notebook, you've got to go up to the top and run every segment, okay? Because nothing's gonna happen and you're gonna get all kinds of errors if you don't. So run all the segments up here first. Just go through and run them all. I already did for mine. Because they look like they've been run, but they have not been run on this session, unless you did it before class. Okay, so run all the way down till we get to where we're plotting the image. Okay. Okay, so whenever you're done with running it all, we plotted all the way down, then make sure that you have this code running, right? This code runs good. Ooh, look at that, it's so dark. Yeah, boot. Another boot. Doing another boot. So make sure that you have this code running. Can you see everything? Do you want me to make the screen a little bigger? You're okay? Okay. All right. So what we should do as well is look at the values of the pixels. Okay. So right now, let's see. Let me run this one more time here. Yeah, interesting. Hold on a sec. Hey guys, when you run yours, what are the numbers on your color bar?
0 to 250.
Yeah. So I already ran the next line down here, which means that I changed my numbers to go between 0 and 1. Okay. So if you look down here, the next lines that I want you to run are going to change your numbers instead of going from 0 to 255. So every pixel in the image, when you first load up this data set, goes from 0 to 255. Okay, every pixel. And we want to make them go from 0 to 1. So you divide them by 255. Okay, and when you do a division like this, it's going to just divide every element of the matrix, right, of every image. Very convenient. So remember that training images, like for instance, the test images are 10,000 of them, 28 by 28. So when you do this, use this syntax right down here, test images divided by 255, it divides every single value in that giant three-dimensional matrix by 255. Okay, which is what you want. It's very easy. You don't have to loop or anything to do it. Very much like MATLAB does. MATLAB does the same kind of thing. Okay. Is that clear what's happening? Yeah, Haley?
I went to update my code because I didn't quite copy everything over at the time when that was happening. And it's giving me errors and I'm not sure what I did.
Can you let me stop the share real quick?
Sorry.
No, it's all right. Oops, sorry. All right, go ahead and share your screen. Let me see. Okay, let's see. Name error. Random is not. Oh, yeah. So if you go to the top of your thing, go up to the top. Keep going. Okay, we needed to import random. So let me go back to mine. Give me a sec. Yeah, let me just go back. You can't see my screen, but I gotta go remember what the syntax is.
I can let you. I can let you share your screen again.
No, you're good. So just type in right under your import matplotlib pylib as plot, this thing line down here, number 2. Go down to number 2 there. There you go. Right after that line, you want to type from NumPy import random. Okay. Now run that code, run that block. There you go.
And then go all in order.
Now if you run everything, you have to keep going down, run down, and I think you don't need to run everything again, but run it again for safety's sake. This is the one downside of these notebooks is this, right? Because if you were had another piece of code that was all in one file or something, it would there you go. You wouldn't have to rerun everything like that. It's a little annoying. But anyway, okay, let me share my screen. Okay. Yeah, I'm a little confused, to be honest with you, because I'm not a big Python user anymore. I used to be like a big time Python user because I would write everything that was slow in MATLAB in Python in it and run it from MATLAB. But I just haven't used it in a long time. But I'm a little confused about why, we imported the whole NumPy library, why we have to now import random, I'm a little confused about that. Like, why isn't that part of the NumPy library? Couldn't tell you. Okay, because it obviously is part, right? Because we said import from NumPy, import random, right? So why wasn't it just included when we imported NumPy? Again, it's been a while. Okay. All right, so we're dividing here, just like in MATLAB, when you divide a big matrix by a number, it divides every value of that matrix by that number, right? So I had already run this. So when I do a plot here, it's already between 0 and 1, right? Okay, so is everybody clear on why it's in color right now? Why is my image in color? You okay, Tyler? Do you need me to make the screen bigger? You look like you're squinting at it.
Is it depth?
No, I'm fine.
Okay. So do you mean like in the picture that the the value is kind of like this coming out of the screen?
Yeah, kind of like a topographical map where
Yes.
it's like the brighter it is, the closer it is.
Absolutely, yes, indeed. So right, and yellow is higher up, which means a 1, right? The highest you can go is a 1, according to mine, right? And if you go back and run yours now that if you've executed line 12, block 12, you go back and execute block 11, the plot, you'll see now it's between 0 and 1, not 0 and 255, right? Make sense? Okay. All right, now let's make another type of plot. Okay. So here we're making plots, and they do it when you use matplotlib. You have initialize a figure, okay, and it's your 10 by 10, and I don't remember what fig size means. It's not the number of pictures or anything. That's a different thing. So I think it's just like how big is it going to be on the screen? I just don't remember. I used to use Plotlib all the time, but now I don't remember anything. But anyway, and then we're going to loop through. And range 25 just means go from 1 to 25, or 0 to 25. Remember, everything goes from 0. Okay. And then it says I'm going to use, this is like the MATLAB command subplot, and subplot says give me a 5 by 5 array. And then for instance, the first one I will be 0 in the first time it goes through, and it'll be 5, 5, 1, which means in the first space. So 5 by 5 array in the first space, and I think it goes across like rows. I just don't remember, but goes across like this, like that. In the first space, now do what I tell you to do, like plot stuff. And so the first thing it does is it makes the y ticks and the x ticks empty, because it doesn't want to clutter up all the all the plots with little numbers on the sides, right? Which are irrelevant to us. We don't even care. They are. And then it turns off the grid because you don't want a grid on there. And you know, if you notice, I'm gonna scroll up for a second. So if you're typing, give me a sec. So if you notice here, the grid is on. That's only because I turned it on, just to see what it looked like, right? See grid, you can see the grid on here. But if I now make this false, then there's no grid, see? So they're turning the grid on and off. So they turned it off on here. And then IM_show is that same command we used, right? And if you notice, I want you to look at this IM_show. It's the training images I, so it's the first image would yeah, right? The first 25. This is the first 25. Okay, now we're gonna go up here. Just look for a second, right? And you have IM_show again, same thing. But notice there's a second argument in IM_show down below. I'm gonna see if I can make this bigger so you can see more, see? So down here, there's a second argument. Very much like MATLAB, then this plot library can work if you have multiple inputs or one input, all right, depending on how IM_show works, right? So you might have one input, and in one input, what do you think it's doing? What's different between, say, this image and this image? What's different here and here?
There's not the same level of light coloration in pixels.
Okay, so there's color up here and there's black and white down here, yeah? Okay, so what is different about the call to IM_show here and here?
Below it's sort of a like a dictionary of like all the possible options. I don't know, like a list of all the possible options.
Well, look at what it's calling. It's calling train images, and then which is just an index. Remember, we said which is this random integer between 0 and 60,000 because there's 60,000 images and we're just picking a random one, right? And that's what which is. Here, the index is I, and that's here. So first time comes through, it'll be 0. And so training image 0 will be literally the first image. So if we like comment this out over here and just which equals 0, and let's see. There, see, it's that Nike boot. I'm pretty sure that's a Nike. Yeah. So the first one is this ankle boot, this weird Nike, basketball shoe or something. Yeah. So I'm gonna change this back. Hold on, give me a second. I like my random thing. Okay. But so what is different here? This call versus this call. Besides the index.
Are you talking about the second parameter? The CMAP equals?
Yeah, the second
POC.
parameter. That's right.
It's,
So the second parameter is what's called the color map. Okay. So up here, we have a color map that says zeros should be dark blue, and ones, things that are closer to 1, should be yellow. And then there's a continuous gradient that goes blue, blue, green, green, blue, green, yellow, whatever that is, yellow, right? Continuously. So that any value between 0 and 1 will have a color value that's in this color map. Now I'm going to do something up here. I'm going to now change my color map by using the CMAP. And notice that gives me all kinds of nice things here, right? So like it tells me color map, and then the syntax is color map equals, and then plot.cm dot, I'm gonna say, I think accent might be the default. No, see, I don't know what this is. I don't know what this color map is right now, right? Because it's a default. And one way you could find out what it is you could go look up IAmShow in the matplotlib. So you want to go matplotlib, Google matplotlib IAmShow, and see if you can figure out what the default color map is. Okay, because I kind of want to know what this is. I want to say, I have to guess. I'm just going to put the accent in and see what that is, but I'm pretty sure that's not the default.
It's not.
And what is the default? Tell me.
Oh, I don't know what the default is, but I ran the accent one and it comes out with this really cool color scheme.
Okay, well,
It's
let's
not
run
that
it.
one.
But I want the default. So I'm going to go look for the default. Jackson, look for the default. Okay. Ooh, well, okay then. Yeah, we need the default.
I think it's normalize.
Normalize? Okay. I gotta spell it right. Z doesn't work. Okay.
No,
it doesn't like
okay.
that.
Hold on.
No. Go,
Oh,
yeah.
here,
go-
interpolation.
Interpolation. Okay. Let's see if that works. No.
I think I might be looking at the wrong
You must be
code.
looking at the wrong thing. So Google matplotlib color map, I'm sorry,
Yeah,
IAmShow.
matplotlib.m.
IAmShow.
Yeah.
Yeah.
I
Okay,
think
I'll
this
look it
one
up.
says Viridis.
What?
Viridis.
Oh, okay, hold on.
Viridis.
You can spell that for me in a minute here.
Yep.
Okay, go ahead.
VIR.
Aha. Look. See, when I start typing the right thing, it shows me. That's a good tip, right? Because all the other ones we tried didn't show me anything. So Viridis. This is the default. So when I don't make a call, when I don't have it in there, it just uses the default. So I'm going to now run it with the default, and we should have back our weird, yellow color map. And just for fun, I'm actually going to, oops, sorry, this does a weird thing. I'm going to uncomment and just use our boot for that. Okay. All right. Now I want to show you something. I'm going to use Viridis, but I'm going to do an _R. Okay. And you tell me what happened to the color map.
Was it just like reversed? All the purples turned to yellows and all the yellows turned to purples?
Yeah. So this is also in MATLAB, you would call this, like you would say Viridis parentheses reverse or something. I can't remember exactly what it did, but something like that. And it would do the reverse. So now, right, you can see it's reversed. Okay. Anyway, so when you called IAmShow in this piece of code, it uses its default because you're not telling it anything different. This is very much like how MATLAB works. Okay. But when you want to change the default, you include it in the call. And there are probably many other parameters that you can include in the call to IAmShow. Okay. So if you want to go look those up, you can go look them up. But anyway, we'll leave that on there just because it's nice and visible. I'm going to put it back to my random guy. And I'm going to put it back to my original Viridis. Okay, so let's go down and look at this now. So it's showing me, right, it's getting the training images and it's putting a color map called binary on it. Okay, so what I want you guys to do is, one, look at binary reverse. There's binary reverse, right? Where all the low values are black and all the high values are white, right? And you can go back to binary. But what I want you guys to do is now go find the names of the color maps that you can use in IAmShow and change it to something interesting in this plot. And when you're ready, share your screen. I've done share probably, right? Anyone want to share their screen? Some cool color map you found? Ah, awesome. Ooh, Inferno. Nice. I like it. Yeah, that's one of the color maps. There's one in MATLAB called Hot, which looks a lot like that. Yeah. That's what we use for the bird song. I mean, bird song. Why did I say bird song? That's what we use for the mouse squeaks is the Hot color map. Yeah. Oh. Anyone else want to share? Oh, there's Hot. Yeah, so it's very similar to that Inferno. I wonder what the difference is between Inferno
I
and
think
Hot.
Inferno uses purple too.
Yeah. That's cool. Yeah, so we use Hot, not reversed for the mouse squeaks.
Got one.
Yeah, you got one. Cool.
Plasma.
Ooh, what's that one? Plasma.
Plasma.
Yeah. Yeah. So fun times. Anyway, okay, so let's move on. Let me share again. So you're gonna have to stop sharing there, Haley, for a second.
Yeah, I know. I'm like,
Yeah, I got you.
Zoom's all messed up from this morning. Sorry.
Oh, it's all right. All right. Okay, so now notice that they also plotted the label, right? They made the X label, so the bottom label of the plot, the name of the thing according to the training, right? According to the labels that the humans have put on there, right? Okay, anyway. All right, now we're getting to the nitty gritty. So this is the call to a sequential model, meaning sequential means that the network goes through layer, right, from left to right layer, right? Whereas, there are things like recurrent networks, et cetera, that are a different architecture, but the sequential call is actually building the network. So the first thing is that it builds an input layer by using a flatten function, which just says, hey, my input shape is 28 by 28, right? My image is a 28 by 28 picture of a coat or whatever, right? And now you need to flatten it, right? To a big long string that's 28 times 28 long, right? That's what flatten does. So the input, the first layer is that input layer that we talked about, right? And then we talked about this dense layer. The next layer is a dense layer that has 128 neurons and uses an activation function called the ReLU. Remember we talked about that a little bit? The ReLU function when we were talking about activation functions. So it doesn't use a sigmoid, it uses a ReLU. Okay. And then it says that the output layer should be another densely connected layer that is 10, that has 10 categories, right? Or sorry, 10 neurons. And why are there 10 neurons? Because there are 10 categories, right? Remember, sneaker, sandal, there was like all these categories, but there's 10 of them, right? Remember that? So this thing that you should type in right now, should be typing in, is the actual network. So the model is the network. So you could call that network if you like, right? If that makes it simpler, you could certainly call it network. Okay, you're building this thing. So now you're building the structure of the actual neural net with that command. So go ahead and enter that and then run it. Okay. All it does, it's not training or anything. It's just building. Let me know when you got that all typed in and you run it. Just that first thing, not the next thing. I'm supposed if you get done quickly, you can type in the next thing.
Same number of data points.
Sorry, my computer just starts playing things on its own. Let me know when you're all done with that one part. Okay, good. Anyone else done?
I'm having trouble reading my screen for the model.compile line. And maybe I've gone too far, but is it logits or like LOGITS or G?
Yeah. Yeah, and then you can type that in, but don't run it yet because we want to talk about that loss function and everything.
Okay, but the logits part, is it S or G at the end of it?
It's an S, LOGITS.
Thank you. My screen's like pixelating it badly, so yeah, sorry.
You good, everybody? All right. Okay. So if you were going to draw this network, right, you'd have, what is 28 times 28? 700 and something, I can remember. Someone type that in, would you? Somewhere.
$784.
784. All right, so you'd have 784 neurons in the input layer, 128 neurons in the hidden layer. There's one hidden layer, right? And then 10 neurons in the output layer, right? That's what your neural net looks like now. Yeah? Okay. So that is what the model, right? That's model, okay, or network. Okay. Now the next thing to do is you compile it. Now you're not really doing anything here. It's just telling the network what you want to use for a loss function, what you want to use for you know, an optimizer, and apparently there are many different optimizers that you can use. So, and this is something that you could go look up. And then the big thing that I want to discuss here is the loss function. So we talked about before, and let me stop my share here. We talked about before, oh shoot, where's my, I don't have my thing up, give me a second. My sketchbook was not up. Okay, remind me later, give me a second. Sorry, it's gonna take me a second. I just gotta share screen and share the right screen. Here we go. Okay, share. And here. Oh, I gotta arrange my screen a little bit better. Hold on. Okay. My pen. Okay, we talked about before a little bit that, or at least you saw in a video, that there is a loss function. That's how you calculate, right? So this is our last example that we came with. But here now we're going to have, you know, x1, x2, all the way down to x, you know, 784, right? Something like that. And so this is m. So this is xm, or m equals 784, right? And then we have the 128 neuron. And then we have 10, which this makes it look like it's the same, but obviously it's not. And then we have the 10 output neurons. Bad, this is bad drawing, but there's 10 of these, there's 128 of these, and there's 784 of these. Okay. And they're all densely connected. I'm not going to draw a bunch of lines in there, but they're all dense. And one way that people use to do that, to say that it's dense, is by using an X, because no one's going to draw a bunch of lines like up here, because it's a pain in the butt, right? Okay, so so what we haven't really talked about too much, except for in the video, was that there's a loss function that you need to optimize, right? Remember, that is the thing that we're going to be optimizing using gradient descent, right? So we need a loss function, and the first loss function that we saw on the video, I think, was the square loss, where the hat, so y hat is the predicted, the thing that the network predicts, and y is the thing, the ground truth, right? Okay, it's a squared loss. So this is called the squared error loss. Okay, and then you when you finally use this, it is average. So this is you can do the average. So 1 over, you know, n train, the sum of yi minus y hat I, where this is going from I equal 1 to the number of training and train. I know this is hard. I don't know why my thing is writing so, I'm writing it's not very straight. So there's a number of training images and then you're averaging over all the training images, right? That's the squared loss that you're doing. Yeah. But there are other loss functions, and like for instance, there's one called the binary cross entropy. And we're not going to be using the binary cross entropy, but it's basically the same. The one we are going to use in this example is basically the same. Okay. All right. So we're going to do L and now the loss, and I'm just going to write it for 1. Of course, the end would be averaged, but we're just writing for 1 would be Y, right? So the ground truth times the ln, so the natural log of the predicted value, plus 1 minus Y ln 1 minus Y hat. This is called the cross entropy. And it's called cross entropy because it actually has the form of an entropy from information theory. Okay, and the reason that people use this, it's pretty important to know vaguely why, is that you get a bigger loss when you're farther away from the ground truth than if you used the square entropy. I'm sorry, the square loss, right? Squared error loss. You get a bigger loss, so you have a steeper function which allows you to get down to the minimums faster. So people use this thing called binary cross entropy. And what we have, let me go back to our, I have to switch screens. I gotta go back. Okay. Why cannot I see this? Give me a second. So what we have is called the sparse categorical cross entropy, and it's basically the same. It's just in spirit the same as this cross entropy, just slightly different because instead of having a binary classification, we don't have, you know, is it shoe or not shoe, right? Right? We have, is it a shoe, shirt, you know, pants, whatever, right? Coat. So we have to use a categorical version of the cross entropy, but that's what that loss function is. Okay, so when you type that in, this compile just means that, you know, set it all up for me with all the parameters that I need for this network. Okay, I don't know the ins and outs of what compile actually does, but you can now type this in and run it. And when you're done, this fit is literally where all that, you know, all that machinery that is, you know, gradient descent, back propagation, all that stuff is in that call to model fit. Because now that trains the, it trains the network. Okay, so it's going to use the training images and the training labels. And of course, with that particular loss function, that particular optimizer, and train the network to recognize these categories from all these training images. Okay, and it does it in epochs. Remember we talked about, or the video I think talked about the fact that if it's very computationally intensive to do this, so you do it in epochs, meaning you do it in steps. You take a certain amount of the training set, right, and then you train on just that, and that's what the epochs is. Well, so that's not, you don't, in this particular thing, you don't take just 10 images, you're dividing your 60,000 by 10. Does that make sense? So you're taking 6,000 a piece every time you train. Remember? Hope you remember that part. Okay, so if we run it, oh, I already did that one. Run the fit, you'll see, takes it some time, depending on your computer speed. Yeah? Okay, did everybody get yours to run? Okay, good. All right. Yeah, so there's a lot of stuff here I want to go over. Give me a second, I'm just scrolling through here. Yeah. Yeah, we don't have a lot of time yet. All right, so what I would like you guys to do between now and next class is I want you to go look up this compile, right? And see what these different things are, like the atom here, the different loss functions, see how you would call a different loss function. Okay, because what we want to do is is mess around with excuse me, boy, I can't talk today. Mess around with the different loss functions you can use and mess around with the different network architectures as well. But the next thing that we're going to do is we're going to understand how well the model worked, okay, once it's been trained. And we're going to do that by looking at the test images, okay, and see how well it did on that. Okay. All right, so I want you to make sure that you've messed around a little bit with it. So meaning, can you get it to use the square entropy? I mean, the square error loss or something, right? So go and look up. You have to go and figure out how to look that up in TensorFlow, okay? And see if you can get it to run with a different error function, okay? Or a different loss function, sorry, different loss function. Bye next time. Okay. All right, guys. We're gonna end a little early because yeah, there's got it. All right.
See you.
Bye.